Welcome to my second lecture on the topic of deterministic neurosyllogistic reasoning. Okay. Last time, I introduced a novel neural network called sphere neural network. It can reach the rigor of syllogistic reasoning. The, mag the magic behind is that it uses a transition map to construct Euler diagrams in the embedding space. To argue this network reaches the rigor of symbolic syllogistic reasoning, we need to prove that for any satisfiable reasoning, this network is able to construct an Euler diagram within m epochs, and this m should be proven. So today, we shall introduce the control process and show this control process has a feature of m equals 1. It's a very strong conclusion, means the network only needs to do one iteration. If the reasoning is satisfiable, it will construct a model, otherwise there's no model. So the method behind is the network uses or implements the method of reasoning through model construction and inspection. It means it explicitly constructs semantic model in the embedding space. And the feature M means it is able to construct model within maxima m epochs if the model exists. Okay, and with this feature, it can prove unsatisfiable conclusion. So if it failed to construct a model in m epochs, then the conclusion is unsatisfiable, and it can conclude the negation of this conclusion is valid. Let's take an example. If we have two premises, some S are M, no T are M, and the conclusion is some S are not T. The question is whether is this reasoning satisfiable? The network first translates into the syllogistic statement into spatial relation between spheres. Some S or M means sphere S does not disconnect from sphere M, so they somehow connected. No T or M in sphere T disconnect from sphere M. Some S or not T means sphere S is not part of sphere T. So let's say if this is the current configuration, the control process will first randomly fix a sphere. Let's say it fixed S. Then it checks the relation between S and M, S and T. If M disconnect from S and the target is they should somehow connect, the network will use gradual descent to move M towards S till they are somehow connected. And S is a part of T. The network will move T away from S. Okay, till part of S is outside T. Then finally, it should optimize the relation between M and T without breaking the already established relation between S and M and S and T. The method is the network will fix S and T and then update M while keeping the relation between S and M. So it will move M away from T as long as S and T are connected. When it when M disconnect from S, the network will repair the relation between S and M first, and then continue to push M away from T. Finally, M's trace like it move around S, and then till a status is disconnect from T, then the network stop by finding a model and conclude the reasoning is satisfied. All the trick behind is this transition map. It guarantees the neighborhood transition between two spheres using gradual descent. Today, we will see how to use this network and how to use this network. So the first simplest case is just control process one is called, we apply the graduate transition function of this map without any constraint. So if we have n minus one statement, and if it's without a loop, then it's easy to implement. We can initialize two spheres that coincided. If this is the target relation, it's done. Otherwise, we can using gradual descent transform to its neighborhood to the target till it satisfies the relation and stop. And they continue because this kind of operation is guaranteed by the transition map, and its relation will not affect already established relation, so it can always move on. The limitation of control process one is it has no constraint. In syllogistic reasoning, sometimes we have the constraint. Well, let me, you see here, process, limitation process one. For example, if we have a target configuration, sphere B should be inside A, and sphere C should disconnect from B and also inside A. If the current situation is C is outside A and B is inside A, then we need to push B towards A until it's inside A. And the control process one will simply push it A, and then the C will connect with B and then violate the already established relation between B and C and then stuck into a local minimum and stop. So how can we optimize, say, improve a loop? Let's think about the case with numbers. Suppose we have 3 points and 3 distance between them. How can we construct a triangle satisfying the 3 distance relation? That's what we are familiar with. We're just using a compass or ruler. First, create a segment between A and B, and then we draw 2 circles. All possible points of C will be located at the boundary of this circle, and then we draw another circle. All possible location of these points with distance T2 to B is located in the green circle, and the intersection point is what we are looking for. And now we do not have numbers, we have qualitative relation. That'd be D, PO, or proper part equal an inverse proper part. So we were also looking for these possible locations. So let's question. If we have a sphere, let's fix it. What are the possible central points of another sphere that disconnect from A? That's quite easy to answer. If anything, any point outside of A exclude it's located on the boundary, we can find a very tiny sphere that is disconnect from A. Okay. All these green area are possible locations, except the boundary of A. And we continue to ask, if we fix the sphere A, what are the possible central points of another sphere that is part of A? And of the second sphere should be smaller than A, but any central point, any point inside A, we can find a tiny sphere that is located inside A. So the possible central points will be inside A. Actually, the third question is, given the sphere A, what are the possible central points of another sphere that contain A? In that case, any point in the universe, we can draw a large sphere. The radius is, say, the distance between the central points plus the radius of A, then this big sphere must contain A. So it's a whole universe. Last question is, given a sphere, what are the possible central points of another sphere that is partially overlapped with A? It's a little bit tricky, but it's not difficult. We can see anywhere in the universe we can draw a sphere. Let's say if this point is outside sphere A, we can take this point and the distance between the central point of the radius, then this sphere is definitely partially overlap. If is inside, as long as it's not in the center of A, we can always create one. So the answer is any point except the center of A is the possible central point that we can create a sphere that partially overlap with A. So we see the trace of these points. It can be convex or concave. In the case of concave, it's the whole universe and then exclude the sphere. Or the sphere can be radius with zero, it's just a point. But anyway, it's a concave. So in the case of how to create what kind of movement should the sphere C take, it's what we need to do is that we need to move C into A while keeping the relation between B. It should disconnect from B. And this means the all possible points of C is a concave space, is the whole universe by removing the sphere of B. It's the left upper side. If the C is the dotted circle and its target is the right button and location, we need to move it to the target without touching the white area. What you need to do is that it should move towards it and rotate around it and then shrink it. Okay. It's rotate, and if the possible location of central point is a concave space, then we don't need a rotation, then we just move it. So in the case of C, we need to um, move inside, and then if it touches B, we should repair it and then rotate around it. Okay. We can see the gradual descent, normal gradual descent plus rotation is necessary and also sufficient to construct polar diagrams with a loop. Then, so the second control process is, we call it, is to optimize the relation between Z and X, and we need to, while keeping the relation between Z and Y. And keeping this relation means if the relation is broken, the network should repair the relation first before move on to optimize the relation between Z and X. Okay, so in that case, if Y is inside X, fixed there, and Z, sphere Z is movable, it's discrete from Y, and we should keep this relation between Z and Y and moving Y inside X. Okay, if the target is Z should inside X, so it move towards it and then rotate around it. And we need to implement this rotation as a kind of gradual descent process. Then it is a neural network, neural process. So we just implemented this process. We call it constraint optimization process of sphere Z um, to optimize the relation between Z and X while keeping the relation between Z and Y. What we need to do is that we need to compute the loss function as the sum of the loss between sphere Z and sphere X, and the loss between sphere Z and sphere Y. Okay, if the sum of the loss equals 0, then we find a location of Z. If during the process the loss between Z and Y is greater than 0, and we should repair their relation first. Means we need to graduate descent the loss function between Z and Y till it's 0, then move on to continue to graduate descent the value of the sum. We need to prove that the reparation process after the reparation process, the sum of the two losses is still less than before the reparation. Okay, so in that way, it's still gradual descent. And then if after reparation, the loss is equals to the loss before reparation, and if this is greater than 0, then this process will stop and say there's no solution. We need to prove this. Let's look at an example. If we are moving sphere Z towards sphere X, and then it touches sphere Y. First, the loss between x and z is the red segment. Okay, it's L, it's a reduced value. However, this increases the loss between y and z. So this is reduced and this is decreased. And now we need to repair it, repair the relation, the loss between y and z. So the process will push z away from y till they exactly disconnect. And this process will increase the loss between y and z. And the increased loss is apostrophe. So the loss between z and x increase, and reparation means the loss between y and z equals 0. And we need to prove the after reparation, the loss still reduce. So this means the L after reparation will increase some value. This increased value is L multiplied cosine alpha, which would be less than L. Therefore, the process is decreased because we assume this 3 century point is not on the line. What happens if we allow the radius of that sphere Z change? It's clear. Let's look at again. If during the process the radius of Z increase, this means this must reduce the value of between the loss between y and z. In the worst case, this would increase the loss between x and z. However, if we look at the delta function, all the delta function is linear to the value of radius. So even if it increase the value, the loss between x and z, the increased loss will be equal to the reduced loss between z and y. So they will be equal in the worst case. Therefore, for the overall process is still a gradual descent. So let's look at an example if we to understand how this process work. So let's look at a case that there's no solution. Suppose we fix two spheres, x and y, they are disconnected, and sphere z is inside y, and this relation must be kept. And the target is move sphere z inside sphere x. This is impossible. Let's see how the process of constraint optimization make the sphere 0 move. First, it will reduce the loss between x and z. It should push forward. Okay, and here is the loss between z and y exactly equals 0. If we continue move, the relation between z and y will be broken, and the network will repair this relation first. They port it back. Okay, and then continue, port it to x, and the relation broken, it ported it back. and this is zigzag process. In the end, the central point of 3 sphere will be located at the same line and it stop because the loss is still greater than 0 and it not reduce. So the overall movement of the sphere Z is like it moves around the inside boundary of Y and moving towards X. When the 3 central points are located at the same line, the reduced loss between Z and X equals the increased loss between Y and Z. After representation, they just balanced. So they stuck to a non-zero loss and the process stopped. Okay. In process 2, we fix the 2 sphere and then to find the location of the 3rd sphere. If the first fixed 2 sphere, the relation is negative, for example, negation P, then it is possible that although the 3 relations are satisfiable, with the process will not, the control process 2 will not find the solution. The reason is the negation relation is incorrectly realized. We can understand this easily through an example. If X sphere is not part of Y sphere, is realized as partially overlap, then it's not possible to find the sphere Z that disconnect from X but contains Y. Okay. This unsatisfiability follows the fact that the X and Y, the partial overlap relation, is not consistent with the other 2 relations. So this can be easily repaired by restart the process and by fixing another sphere. For example, if we fixing Z, then Z disconnect from X, it will push the sphere X away from Z till it's disconnect. And then Y is already inside Z. In that case, the relation between X, Y is correctly realized. X disconnect from Y is certainly X is not part of Y. So the 3rd control process is restart the process by choosing a different sphere to fix it and to optimize the other 3 relations. So the proof process is to show that this control process, one iteration can construct a model with necessary one restart. Let's let me put this on the right place. The strategy behind is that if we have a function greater or equal than 0, and it's a gradual descent, and then if we can find a value x star, this function returns 0, then for any x0, any value, we can using gradual descent process to find x apostrophe 0 such that the function will return 0. We start with the first corollary 1, we observe all our gradual descent function or delta function is the linear function of the radius and the distance between the central point. Okay, and then with this we can with this transition map we can easily prove the first theorem that for non-cyclic syllogistic statement, our control processor 1 can create a model without any problem. And we just follow the procedure. The new created relation will not destroy or affect the already established relation. And the second observation, or very easy provable feature, is that the rotation process will preserve the value of loss function and certainly preserve their qualitative spatial relations. The reason we see is that rotation will not change the distance between the central point and also will not change radius. So then we can show rotation. We need to prove rotation is enough, sufficient to relocate a sphere while keeping its relation to another sphere during the process. For example, if we have two spheres, V and W, and we want to relocate V from location A to location B while keeping its relation to W. If V must be inside W, then it's obviously we can do directly moving the gradual descent, and because the possible central point while keeping its path relation is convex. It's just the circle of W. If V should be disconnected from W, and while W is stayed in the middle of the current location to the target location, then we need a rotate at the right time. And then continue. Okay, this is lemma 4 talk about. And then we just showed that the constraint descent, the constraint with optimization process is the gradual descent process. So then we need to find the X star. We need to see that if these constraint relations are positive, then there is a configuration that the global loss is 0. So let's say if we have three configurations, so we have three relations for three spheres. And if all these relations are positive, means they are D, PO, and PP equal and contain. What we want to show is that this configuration satisfiable means there exists three spheres in the space, okay, satisfy the three relation. But what our control process does is to create them in a sequence. It does not create three spheres simultaneously. We need to prove if they're satisfiable. And our there is a configuration that follow our control process, we can find it. Okay, so we need to say there is we first find two spheres satisfy the relation, and then we need to find x star, means we need to create the third sphere that satisfy the other two relations. Okay, this is x star. And we prove the existence by create them. Okay, let's see how to create them. We take one example. If we have three spheres, x sphere 1, sphere 2, sphere 3, they satisfy three relations. X1 partially overlap with X2, and X3 disconnect from, sphere 3 disconnect from sphere 1, and sphere 2 should contain, or properly contain sphere 3. What we can create is that we connect their central point, and then this segment intersect with the boundary of sphere 1, the P. And then we extend this line, intersect with the boundary of sphere 2, point is Q. Then we randomly select a point A between P and O2, and select another point between O2 and Q. Then we draw a sphere, take the AB as a diameter. This is O3. Then O3 is proper part of O2, and meanwhile disconnect from O1. Okay. This is the case of three relations are positive. What if there's one relation is negative? So what if R3 1 is a negative relation, and not D, not P, or not inverse P? Actually, negation relation can be understood as disjunction of positive relations. So, and this we can enumerate as the disjunction of positive relations. So it's a directly conclusion from lemma 1. As long as the three relations are satisfiable. Then we can, so we have a fx is greater 0 and gradual descent, and we find a specific kind of x star equals 0. So put them together, we have the first lemma, say, in given this condition, say, the control process can create a model in one epoch. If the first target is positive, first relation is positive, and the second relation is positive, the third relation can be positive or negative. This is lemma 5. So what if the both relations are negative? This means we first, the relation between O1 and O2 are positive, and then O3 have both negative relation between negative relation with O1 and O2. Actually, it's an easy case because we can take a special relation, say partial overlap. Partial overlap is not D, not P, and not an inverse P. And the method to create O3 that partial overlap with O1, O2 is to let its boundary to pass the century of O1 and O2. It's quite actually a simple solution. in either case, we can find this X star that satisfies the three relations. Then we extend our the power of our network, that is, it's provable also for the second and third relation are both negative. Now the case is that put them together, we say if the three relations are satisfiable and if one of the relations is positive, and then our network can create this relation first and using constraint optimization to find the third sphere that is satisfy the other two relations and then find them out in one epoch. The question is, what if the first relation is negative? Okay, we have shown this will cause problem and need a restart, and we need to prove we only need once to restart once. So let's look at example. If O1 and O2, their relation is negation D and it's realized as partially overlap. And O1 is part of O3 and O3 is part of O2. In that case, if we fix O1 and O2 as being partial overlap, it's not possible to create to find O3 using our constraint optimization process. The reason is that partial overlap between O1 and O2 is not satisfiable with the two-part relation with O3. So this means, this means from this point of O3, if we take the relation between O1, O3 and O2 and O3 as premises, these two premises will be inconsistent with the PO relation between O1 and O2. This unsatisfiability means the two premises between O1, O2 and O2, O3 will deduce a valid conclusion between O1 and O2. All right, this means if we fix O3 first to create one O and one sphere 1 and sphere 2, the relation between O1, sphere 1 and sphere 2 will not be partially overlapped. They will deduce a valid relation. Okay, and we call this valid relation as R star 1 and 2. And valid means it must be true if the premises are correct, are true. And then what we have in the task is the condition is that the three relations are satisfiable. This means if we starting from O3, it will deduce a valid relation. And what we have is the satisfiable relation. And then valid relation is stronger than satisfiable relation. So this naturally follows satisfiable relation. This means if we starting from O3 to create the relation, to create sphere 1 and 2, the relation between sphere 1 and sphere 2 will be automatically satisfied. For example, we're starting from O3, creating O1 should be O1 is inside O3, and then O2 is contain O3. Then also automatically the valid relation is O1 is part of O2, and certainly follows the satisfiable relation that O1 does not disconnect from O2. Okay, so this means we only need to restart once. Next, what we need to prove is we initialized all the spheres as equal. And then if this is a model, we find it. And if not, in the process of constructing spheres, we will we will exclude the equal relation. This means we need to prove this process will not lose any possibility, any possible models. Lemma 9 says if there is a model, and if one of the relation in this model must be equal, all of the relation must be equal. Okay, if this lemma is true, then our construction method by initializing all spheres as equal, and then after that we exclude this equal relation from model construction. We're not introducing problem, we'll not lose models. And this is easy to prove by using mathematical induction. We look at the case of n equals 3. If one of the relation R3 must be equal, equal means A is part of B and B is part of A. So here R3 must be equal means O(x1) is part of O3, and meanwhile O3 is part of O1. Both part of relation is valid. And if we look at the 24 valid types, if the conclusion is part of a relation and the premises can only be another part of relation, and this causes a nested sphere relation. So O3 is part of O1, I mean the premises can only be O3 is part of O2 and O2 part of O1. And then we replace the order of 1 and 3, we just have O1 is part of O2, O2 is part of O1, so they're equal, and then all three spheres are equal. If we assume the case for K is correct, let's consider the case of K plus 1. It's a loop, and we look at it's a loop, so without generosity, we just assume R1 must be equal and look at the first a triangle relation. Let's observe, we'll introduce the relation between OX1 and OX3. We say it R3, 1. This is observed relation. And then it can be D and PO and PP equal and PP inverse. What we need to do is we need to promote this relation to a syllogistic relation. So if D is still D, that means O1, no O1 are O3. If PO, we need to make it into a negative relation. It can be not D, not P, or not inverse P. Purple part is the kind of part, equal is any is part or inverse part, and inverse part, proper inverse part or proper containment is a kind of containment. In that case, we just decompose the k plus 1 into two loop. First is n equals 3 case. If in this 3-term case, R1 must be equal, then all three relations must be equal. This means R3, 1 is equal. And then it applies to the n equals k case, the second loop, which we assumed if R3, one of the relation is equal, then all of are equal, then we prove the case of k plus 1. Okay. So with using this restart theorem and then the initialization theorem, we have the first theorem, theorem 4, which is the which says the sphere neural network can construct a satisfiable model correctly in one epoch. Maybe it needs a restart in this epoch, but it needs one. It can do it in one epoch. This n equals 1. And this is the description. So we can look at the whole control process. First, we initialize 3 spheres as being coincided. And if this is a model, we find it. If not, we randomly and break this coincidence relation by a small fluctuation. So the equal relation is excluded from the model construction process. Then we randomly choose one, say O's and the first sphere, fix it and update it, create O2 without a constraint, and the same to create O sphere 3. Then we do a constraint optimization to see whether this can be realized. If yes, we find a model. If not, we need to restart the process by fixing another sphere and repeat the process. And now constraint satisfaction. If the global loss equals 0, we find a model. If not, the control process stop, says the 3 relations are unsatisfiable. Now we need to extend the algorithm for long chain syllogistic reasoning. Theorem 1 is actually for all non-cyclic statements, so it can create a model for all the n minus 1 premises. Then for the conclusion between sphere 1 and sphere n, it should fix sphere 1 and sphere n minus 1 and do a constraint optimization. If it reaches global 0, then the final model, okay, the reason is satisfiable. If not, again, we need to choose another sphere to fix it. In that case, we will fix O1, and then to realize to create ON as a satisfying relation of Rn, and then fix a sphere n to update the location and size of sphere n minus 1. Okay, this is okay. In that case, after that, we will promote the relation between sphere 1 and sphere n minus 1 to make it a syllogistic relation. So if before the backward process, the relation between O1 and On minus 1 is dPO PP or inverse PP. These are observable. So if after the backward optimization, this the relation must be changed because the earlier case is unsatisfiable. If the earlier case is D, earlier relation D, we rewrite the new relation as negation D. If the earlier case is PO, we observe the current relation. Any of what we observe is the syllogistic relation. If the earlier relation is PP, we write negation P, and then if the earlier case is inverse PP, we write in negation inverse P. Then we just reduce the case into the n-1 case, and then we can continue backward update. And then finally, we'll reduce the case of 3, and then we know all this process is deterministic. And then we proved our theory that for long-chained syllogistic statement reasoning, our sphere neural network also needs only one epoch. Then the complexity is proportional to the number of turns. So we can look at the proof of cards, okay, that guarantees the network reaches the symbolic level of syllogistic reasoning for long-chain syllogistic reasoning. Any questions? Let me stop recording and then you can ask questions.